All right, so this section is antidifferentiation using substitution. Now, before I jump into how this technique works, I wanted to talk a little bit about something we haven't seen yet, but you guys can, I think, handle just once you know what the lingo is and how it looks and all of that. And that is an indefinite integral. So an indefinite integral is simply this. What's different about this integral from any other ones that you've done? What's missing? Well, okay, pretend there's actually a function in there, because the f of x is just generic for any function. There are no limits, right? There's no lower limit, there's no upper limit, okay? So an indefinite integral is really just another way of writing I want an antiderivative of f of x, okay? Okay, with the plus c on the end and the whole bit. Okay, that's all that is. So if I gave you a problem where I said, all right, evaluate the integral of squared dx, what would be my answer to that then? What is the antiderivative of that? 1/3 x to the third plus c. Guys, have I shown you the T-shirt that my calc class had? I don't know if it was not last year, 2 years ago. Oh, there's a bunch of inside jokes on the back, and one of them says plus C with exclamation points next to it. We put that on the T-shirt because everybody would forget to do that. They'd never put the little plus C on the end of these things. And like, oh, it's 1/3 x to the third. I'm done. No, there's a constant too. So we put that on the T-shirt. Anyway, that's who you can. I'll leave that to you guys. So you let me know, and I will do what I get. The third derivative. Yeah, that was another one. Let's do another one real quick here then. All right, we'll do that just one more, and then we'll move on. So, what about the integral of 2 over x squared plus 1? Doing an indefinite integral of this one. So it's like finding the general solution again. So what do we got? Good. Yep. So it'd be 2 inverse tangent of x. So as long as you can calculate the antiderivative, you can do these. So, moving along, we're going to be looking at doing some indefinite integrals of some functions that up to this point maybe you couldn't do. Maybe you can. Some of these you can kind of riddle through in your head a little bit. Basically, anytime you're doing a U substitution type technique, it's looking at a function that, remember, that came from by doing a derivative, right? So if you had used the chain rule to get to the derivative we're looking at, then a U substitution will make it go back to where it started from, okay? So, like, I'm going to give you one that maybe you can see the chain rule in it and tell me the answer. Maybe not. But I'll show you how you can do this with the substitution as well. So, let's say we got the integral of Okay, so let's say we want to do the derivative of cosine of x squared times 2x. Anybody tell me the answer to that? Just by looking at it? What function, when I take its derivative, would have given me that? Sine what? Sine of x squared. Yep. And then don't forget the plus c. So, how do you know that's the answer?
No, you feel it.
You feel it. I was just feeling it when I came up with that. It just happened. Well, it's a little bit, I guess, without knowing how to do a U substitution, it's a little bit of guess and check, perhaps, knowing that you have a cosine of something, so a sine would be a good place from whence it came. And then if you think about, well, if it was just sine x squared, if I ignore the 2x to start with, if it was just sine of x squared, if I do that derivative, it's the cosine of x squared. But then the chain rule tells me I have to multiply by the derivative of x squared, which happens to be 2x. So it works. Okay? Well, how could I then, without having to guess and check every time? Okay? So in doing a U substitution, you want to look at what has been substituted in. Okay? So step number 1 is going to be choose a U. And you're going to choose that by looking for a substitution that took place. So we'll do this in a minute, but what do you suppose would be a good portion of this equation for a U? What looks like it's been dropped in there, been substituted in somewhere? What part of cosine x squared times 2x? Do we normally take the cosine of x squared? Normally it's just what? Cosine x. So what's been substituted in? X squared. So your U in this case would be x squared. But we'll do that in a little bit. All right, this next step's going to seem a little strange when we actually work the problem. I'll show you why it works. It has to do with the differential. But you want to take the derivative of U and substitute it in using dx. And I'll explain what's going on with that dx in a little bit. And then on those first two steps, you should be able to evaluate the integral now using some kind of technique you already know, or some formula you already know. And it should be all in terms of U now. And then finally at the end, once you have an answer with a U in it, you're going to back substitute. You're going to put that x squared back in. All right, so let's see this process in action real quick here. Okay, it'll make a little bit more sense once we actually use it. So we're going to go for this integral again. Cosine x squared times 2x dx. All right, we already talked about choosing the u. The u we want is x squared. And this is actually the most difficult step of the whole process. Because sometimes you'll pick a u and you'll think it works, and oh, that looks like it was substituted and it's going to work just fine for me. And then you start to go through the rest of the process and you're like, oh crap. doesn't actually work. I'm not getting things to work out. So now I got to go back and choose a different u. And you can kind of spin your wheels a little bit with that. But once you do enough of these and you kind of get the pattern and you're used to it a little bit more, it'll be that much more easier to figure out what's going to make the appropriate, what's going to be a good choice for your u. So with this first one as well, but that's okay. It's the first one you're doing. So, all right, so we had u is equal to x squared. That's what we wanted to make our substitution here. Okay? So step 2, it says take the derivative of u. Okay? So du equals what? What is the derivative of x squared? 2x. 2x dx, though. Now, the reason it's that is because technically it would be this, right? Du dx equals 2x. Right? If I derivative of that little equation, u equals x squared, it would be du dx, right? Because those are the two variables you're using. And that would equal 2x. But all I've done is taken that dx and then shuffled it over behind. It means the same thing. It's just been that part been moved, that little differential. Okay. So then this equation, I'm going to solve it for dx then. So dx is equal to du over 2x. And then I'm going to take this initial little substitution that I came up with, and piece down here that I have solved for dx, and put them both into that first integral that I started with. Do you see how that integral has an x squared in it? It has a dx in it, so I can plop those both into that. So then what I end up with here is the integral of cosine of u, still times 2x. And then my dx we found was du over 2x. Like that. Now if I have picked a good u for my substitution, something should happen here. All your x's should go away. Do you see how that's going to happen with this one? The 2x and the 2x should cancel each other out. And what I'm left with is an integral completely just using u. No more x. So I've got the integral of cosine u du. So if I do the antiderivative of this thing in terms of u, which is step 3, evaluate the integral in terms of u, I can do that, right? I know the antiderivative of cosine. That's easy. I've taken a difficult integral, something that looks complicated, and I've rewritten it in such a way now using u to take the antiderivative of it. What is the antiderivative of cosine? Sine, right? And don't forget your plus c there. Okay, the answer to my integral then is sine u plus c. Well, no, not exactly, because whenever you do an antiderivative, you want your answer to be in terms of x as well, right? The first thing I started with was in terms of x. I want my answer in terms of x. So what's the only thing I need to do now, though? Just put it back in, right? We know what u is. It's x squared. So put it back in. Sine of x squared plus c. You guys see how we ended up in the same spot? Okay? Just by kind of thinking about it back to the chain rule, we were able to reason out that it should have been sine x squared plus c. And by doing a u substitution and working our way through it that way, we got the same thing. Sine plus c. It works. Okay? So, in this, and like I said, the tricky part is that u for each particular one so that it works out. We can do it. So let me find some other ones. Okay, here's a good one. All right, so again, look for what appears to be substituted in. Is there some kind of a function in there in the middle of the bigger function that appears to have something just shoved into it? Okay, so 5 plus 2x to the third is a reasonable candidate for a u on this one. Does that make sense? Because it's the square root of that thing. So if we try that, seems like that would be a reasonable way to go. So let's see what we get. So okay, we'll go u equals 5 plus 2x to the third. Okay, what's my next step? What do I do with that u once I pick it? Do the derivative of it? Okay. So what is du? Six x squared, but then don't forget. Nope. Dx. We're not doing an antiderivative just yet, right? So no plus c on this one. It's just the dx. So what did I do with that then? What's the next step after this? How do I use this du equals 6x squared dx? Take a look at the last example if you need to. Solve for dx, right? Because I want to be able to substitute that back in for dx. So if I solve it for dx, I get du over 6x squared. Okay, so I'm substituting this, and I'm substituting that. Alrighty, so that should take my original integral. And now I have x squared square root of u, and then my dx is du over 6x squared. So like I said before, if I've picked a good u, x's should cancel. Are they going to? Take a look at that equation. I still got an x squared and then another x squared, but what's going to happen? They should cancel, right? I got x squared, and then I'm dividing by x squared. So those are gone. The 6, but who cares? It's not a big deal. And why do I not care about that 6? Well, because technically with that 6 in that denominator, it's 1/6. And I can take a constant and do what with it with an integral? If I have a function multiplied by a constant in an integral, what can I do with that constant? Pull it out front. Yeah. So this then becomes 1/6 of the square root of u du. So I can do the integral of the square root of u, get my answer from that, and then just multiply the answer by 1/6. And it'll be the same thing. Okay. So can we do the antiderivative then of the square root of u? Absolutely. To rewrite it as 1/6 integral of u to the 1/2. So you can think of it like a polynomial, but yeah, we can totally do that. So what's going to be our new power? Careful, I'm doing an antiderivative. 3/2, yeah. So if I've got a 3/2 there, what should be in front of it? Good. 2/3. 1/6 as well, though, right? So don't forget about that. But yeah, So don't forget, at this stage, right, plus c, because that's an antiderivative there. Okay, so 1/6 times 2/3, that would be 2 over 18, which is 1/9. So 1/9. And now I can take my u, do some back substitution, put that in there. Okay, 1/9, 2x to the third to the 3/2 plus c. That's the antiderivative. So, anybody think they could have come up with that antiderivative without using the substitution? Yeah, shut up. No. On that one. There are some, like the last one, where you can kind of reason it through. There are other ones where it's you just got to do it. It's really hard to see otherwise. So about do on your own and see what you come up with. Okay, I think you've got enough knowledge to be able to handle something like this too. Okay, so sin x, e to the cosine x. Think about what's going to make a good u. Where does it appear there's a substitution happening? And then take that process all the way through. See if you can do it. And then we'll move into some, I got some trig substitution ones coming up here. Or we're going to use some trig identities to help us with some more of these after this. right, you guys need some more time? You okay? Okay, good. Those that are done, I want to at least show you what we got here so you can check and see. So that's what I came up with. Yeah, don't forget the plus 3. General. They're all right? Or get through those? Okay. Some of these where we might need to do a little bit of trig identity to help us through it. And identities that you should know at this stage from pre-calc that I'm going to maybe have you use are the following. Okay, so those three for sure. Those are your reciprocal identities. Pythagorean identities. And this first one you've used quite already, but that one might come into play. Then we've got and then this one. Okay, so those are all of your Pythagorean. Oh wait, did I screw that? I screwed that up. Sorry. I wrote these two backwards. Should be like that. And then this one should be 1 plus tangent squared is secant squared. Sorry about that. Those. Okay. So, reciprocals and Pythagorean. Might need that to get some stuff started here as well. So I'll give you an example of integral where we would have to use that sort of thing. So let's say I've got the integral of dx over cosine squared 2x. So to get this one started, find first of all that dx on the top, you could just, it's like being multiplied by dx, you could just shovel it over to the side, and it's 1 over cosine squared 2x times dx, if you're used to seeing it that way. Then we have 1 over cosine squared of something. Okay, what is 1 over cosine? Secant. Okay, so what we really have going on here is secant squared of 2x dx. Okay, now think for a second. We're looking for an antiderivative. Secant squared should look somewhat familiar. What has a derivative that is secant squared? Tangent, right? So we should be able to do this now. It should have something involving tangent as our answer. Okay, we still got to go do that u substitution thing, though. What's going to be our u for this one? 2x. Good. Okay. So du is 2 dx, and then dx is equal to du over 2. So we've got the integral of secant squared u times du over 2 but I'm just going to pull that 1/2 out front. And like we said, antiderivative of secant squared is tangent, right? So this is 1/2 tangent u plus c. But that u was a 2x, so it's 1/2 tangent 2x plus c. Okay, so we're still going to use a u substitution with these guys. Kind of little trig identity thing that you need to use to get it started. Okay, in this case, we used a reciprocal identity with secant to be able to do it. Because I know I don't know of or an antiderivative of cosine, an antiderivative of secant squared. So if I switched it into that, then I had a method that I could go use to do it. Okay. Is there another trig type identity we could use? Yeah. Guys, with the trig. And then I've got, hopefully time. Example I want to do, at least after this one, where we have to do a double substitution. So let's see how it goes here. Squared 3x. Does anybody know an antiderivative for cotangent squared? Nope, not me. So cotangent with that was involving, to quickly go back here, cosecant squared and 1 and all that. Okay, so if we work that, we'll be able to come with something using that. Okay, so this squared then should be cosecant squared minus 1. Right? If we switch it around. So cosecant squared 3x minus 1. So this is the entire thing dx. Does anybody remember the antiderivative of cosecant squared? It's cotangent. So we'll talk about that more in a minute. And what's going to be the good substitution on this one? 3x. Okay, blitz through that real quick. U is 3x, so du is 3 dx, so dx is du over 3. So we've got the integral of cosecant squared u minus 1, and then dx is du over 3. So we've got 1/3 in front. So it looks like that. Okay. So before, the derivative of cotangent was negative cosecant squared. I don't know if you remember that or not, but that was the case. Okay. Derivative of cotangent, negative cosecant squared. So what's the antiderivative of a positive cosecant squared? Negative cotangent. Right. So this is going to be 1/3 times u. What's the antiderivative of negative 1? Negative x, or in this case, because I'm talking about u's. Oh, this should be du, sorry. Should be negative u, right? Because we're doing everything with u's right now. And then plus c. And then we were going to substitute our 3x back into there then, and that should be it then. So 1/3 negative cotangent 3x minus 3x. I guess we could distribute our 1/3. That would make it a little nicer. So negative 1/3 cotangent 3x minus plus c. So I distribute that 1/3 into the 3x, it's just x. And there you go, using one of those Pythagorean identities to get myself started on this one. Okay, so be careful with those, trying to pick one. Usually it'll jump out at you a little bit, but you might have to try before it works out for you there. But so double substitutions. Got a little bit of time, I think we can do it. Alright, let me find one here we can do with this. Yeah. This one, we can go ahead and pick our u and do that whole bit. And then once we do that, though, you're going to still have something you can't evaluate yet. But if you repeat the process one more time, you can. Okay. So, to get me started here real quick, what should be my u? So u is 2x plus 1. du is 2 dx. So dx equals du over 2. Okay, so then my integral becomes sine of u divided by cosine squared of u. And then my dx is du over 2, but I'm just going to go ahead and take the 1/2 and pull it out. Pretty sure you guys can follow me there, right? It was du divided by 2, so technically the 1/2 could come out front. And now I've got sine over cosine squared u du. I've canceled all my x's. Everything's good to go. Oh, but it's sine u over cosine squared u. I don't know how to do that. I don't have an antiderivative for that, even though the cancellation stuff all worked out in my favor. Well, we got to go again. Instead of u, we'll use a v or some other letter. Okay? We need to make a second substitution somehow. So just ignoring the first one, but just looking at where we're at right now, does anybody see something where we could make a substitution that might work? And this one's, it's a little trickier. It's hidden a little bit more. You're close. Nope. Just the cosine. Just the cosine. Here's a hint for you guys. Notice how whenever we take a u, we end up taking the derivative of it, and that derivative cancels with something else, right? So I want to pick something where the derivative of it is in there somewhere to cancel it out. If I, instead of just take the derivative of right up here, and it should cancel that out. Okay? So let's try v equals cosine u. All right, so v equals cosine u, dv is negative sine u du. So the du is dv over the negative sine of u. Put all that in there then, okay? So then this is going to become 1/2. The integral sine u is still there, but I substituted cosine with a v, so this is going to be v squared on the bottom there then. And my u is all this stuff. So du over negative sine u. Do you see how the derivative is going to cancel, just like I said? The sine and the sine will cancel each other out there. And now no more u's and just v's. Oh, this is a v. Sorry. Screwed that up. It's supposed to be dv over that. Okay, so we end up with 1/2 the integral of dv v squared. But this sign here was negative, so I'm going to make that negative out front there then. Just pull that out. So it's negative 1/2 dv over v squared. We can handle that. So think of it this way. Negative 1/2 v to the negative 2 dv. Okay? So the antiderivative, I got to bump this power up, right? Which would put it up to negative 1. So I've got negative 1/2 v to the negative 1, except, oh, that would have to be a negative in front to cancel that negative 1. So instead of negative 1/2, now we're at positive 1/2. So v to the negative 1 plus c would be that antiderivative then. But now I got to back substitute. And now I have to do it twice, right? Once to put the u's back in, and then after I got the u's in there, then I got to put the x's back in there. So we'll go through that process. So it's 1/2. What was v? Well, v was cosine of u. So 1/2 cosine u to the negative 1 plus c. And then I got, okay, but now I got to back substitute for my x. Well, what was the u equal to? That's up all the way up here. U was 2x plus 1. So I got to pull the 2x plus 1 into there now. And then I'm finally done. So it's 1/2 cosine of x plus 1 to the negative 1 plus c. Okay. So you can do it, but you want to keep looking for that thing to substitute. Okay? Enough to get yourselves going. Remember, please read through the section, though. I did steal a couple of examples from the section, so you can skip over those. I'll read through the rest of it. It'll help you. Okay? And course site's ready to roll for you.